So thank you so much, everyone, for taking the time to join us today. I am Aisha Wu, the Communications Officer for the Alberta Land Institute. The Institute aims to connect research and policy for better land management on Alberta's changing landscape. Today's webinar is part of our Lunchtime Land Use webinar series. The goal of these webinars is to encourage knowledge sharing and discussion about a variety of land use topics relevant to Alberta and beyond. When speaking about land use, it's important to acknowledge that the University of Alberta, its buildings, labs, and research stations are primarily located on the territory of the Nihil, Niitsitapi, Métis, Nakota, Dene, Haudenosaunee, and Anishinaabe, lands that are now known as part of Treaties 6, 7, and 8, and homeland of the Métis. The University of Alberta respects the sovereignty, lands, histories, languages, knowledge systems, and cultures of all First Nations, Métis, and Inuit nations. I'm going to pass it off to today's moderator, Sandeep Agrawal. Sandeep is the director of the Alberta Land Institute and a professor in the School of Urban and Regional Planning at the University of Alberta. So go ahead, Sandeep.
Thank you. Thank you, Aisha. Hello, everyone. So today's webinar will focus on how the increased snowfall that we have seen this winter may impact drought and agriculture in Alberta. And again, I'm saying increased snowfall, which is a bit of a rarity these days. But it's an interesting topic from my perspective, and we have two presenters who are experts in this field, and they will present their PowerPoint slides, and then we'll have a Q&A after that. So if you have any questions during the presentations, you can put them in the chat, and Aisha will add them to our Q&A question list. Or you can raise your hand during the Q&A and you can verbalize your question. So our first presenter is Phillip Harder. And you can see him on the screen. He is the VP of Data Science at Croptomistic Technologies, Inc. Phillip grew up on a family farm near Saskatoon. He studied hydrology at the University of Saskatchewan, earned his PhD in 2018. His research interests focused on understanding the relationships between snow, hydrology, and agriculture on the Canadian prairies. So the overarching motivation of Phillip's current work is to develop and deploy precision agronomy tools that meaningfully improve agricultural outcomes and reduce water-related risks for Canadian prairie producers. So, Phillip, take it away. Love to hear what you have to say about precision agriculture as well as today's topic. Thank you.
All right. Well, thank you for the invitation. Can everyone hear me? We're good to go?
Yes, we can hear you.
Excellent. So yeah, I'm going to just sort of kick things off, I guess, with a little bit more of a broader background in terms of how snow and agriculture kind of interact from a sort of hydrological process perspective. So I'll just sort of start off with, I pulled these maps from the Alberta Agriculture Climate Information Service, I believe it's called, where they've got some products that are available to show, where things are at in terms of agroclimatic situations. And this is just kind of an interesting figure. So this is late February, and on the left is the snow water equivalent, the actual values. So it's ranging from basically nothing in the south up to more than 150 millimeters of snow water equivalent in the Peace Country. And then to put that into the context of, average conditions, that's the right figure. And we're going from clearly much below normal up to much above. So depending on where you sit in Alberta, you're going to have a different perspective on, where snow conditions are at. And so my talk this afternoon is primarily just to try and help you understand the implications of these snow, how much snow matters to agriculture, I guess. So as a hydrologist, I tend to look at the landscape in terms of the water balance. And so we have precipitation that comes in to our, control volume. In this case, let's just pretend it's a unit square meter of soil in the middle of a field. So we'll have water that comes in via precipitation, and then we lose it through evaporation from the soil and transpiration from our crops. But it's not just one-dimensional. We have got runoff that comes in and out during the summer, interflow, so that's the subsurface lateral flow, and we may or may not have interactions with our groundwater. The fun part in all of this, when it gets to the Canadian prairies, is that we also have this wonderful thing called winter, where we have a completely different set of hydrological processes. So instead of rainfall, we have snowfall, we have snowpack that accumulates, but we also have sublimation from a snowpack, which we may or may not recognize. And then we've got all these blowing snow processes. So from an agricultural perspective, we want to increase crop production, which really at the end of the day means we want to increase transpiration, which really comes down to how can we manipulate hydrological processes from this sort of overall conceptual framework to maximize crop available water. So kind of talk a little bit more around some of the snow processes and guess the implications of and their importance. So some of the work that I did my grad studies and postdoc at the University of Saskatchewan. So one of the things we were working on was directly monitoring and measuring the water balance of the growing season. So the top two rows, these are sites that are near Saskatoon. And then the bottom two rows are a site that's a bit further south of Saskatoon, about an hour away. But what this is really trying to boil down to is how much water is used by a crop. So in this case, we were measuring crop evapotranspiration. The red is the cumulative amount over the growing season. And then we were also measuring the rainfall that occurred at those sites. That's the blue. And then also looking at soil moisture change from, I would say, a insufficient number of soil moisture probes. But the key thing to pull out of this is that crop water use consistently, there's a couple of years at the beginning which were yet wet years, 2015 to 2016, where we had crop water use equivalent to our rainfall observed during the growing season. But we also had a lot of years where we don't have, so high rainfall rates, and it's very clear that we have a lot more crop water use than comes in the form of rainfall during the growing season. So the blue bar consistently, after 2017, consistently much less than the crop water use. So there's a gap here. So soil moisture is obviously overcoming it, but we weren't measuring it very well because this is the evapotranspiration is an aerial average, whereas the soil moisture change in this situation was much more point data. The long story short is we had some years where we had significant crop water use. 2017, this canola used over 200 millimeters of water, yet we only got 60 millimeters of rainfall. So where is that water coming from? It's not magical. It's not coming from some unknown source. The reality is it's coming from our non-growing season sources, specifically wintertime snowmelt. And so when we look at growing conditions, we often tend to focus on just what is the rainfall condition, but it's not doing a lot of the justice to how much snow actually matters. So this is kind of a very complex process, and how these snow conditions and soil moisture factors and how these things change over the course of the year. It's a very non-linear system, which creates uncertainty, complexity, that kind of gets in the way of good predictions. But we'll go into this a little bit more detail later. But for starters, we have these interactions between our snowpack. Snow has this insulating effect, and so if you have no snow, we have freezing front that decreases or penetrates into the soil a lot faster. So if you have snow or not, that changes how far your soils are freezing. How far your soils freeze dictates how long it takes for them to thaw in the springtime, and how that will influence frozen soil infiltration processes, which are important. And what's more, kind of the wild card in all this is what happens in the middle of the winter. So if we have a midwinter melt, where we've got a decrease in our snowpack because it's melting and then basically flowing through our snow and reconsolidating at the surface and refreezing, we can get this very nonlinear response where we don't have a lot of infiltration all of a sudden. So there's a lot of factors in play, which makes it very dynamic, makes it very interesting to study, but it's also hard to, plan around if we want to think about it from the agricultural perspective. So I'll kind of pick off a couple of these things. And the first thing to realize is that there's a lot more water in snow than we sometimes give it credit for. Often we'll hear on the radio or weather channels where it'll be like, oh, we get 10 centimeters of snow, that equals 1 centimeter of water, which is fine for freshly fallen snow. But as snow forms into a pack and changes over the course of the winter, the midwinter melts, as things get blown around, snow density increases significantly. So a 1 to 10 ratio, that's great for freshly fallen snow. But in reality, we get into sort of, springtime conditions, and in Saskatchewan, we frequently are seeing about 35% snow water equivalent or snow density. It depends on the conditions you're in, but there's a lot more snow. There's a lot more water in snow than sometimes it is given credit for. The fun fact about snow is that it is also one of the main precipitation factors that we can actually manage. So snow, unlike rainfall, which will fall on the surface and either will infiltrate and run off very quickly, snow is this temporary storage of water on the landscape, and it blows around. And so there's a lot of physics that is important to understand, but I think one thing to kind of simplify the process a bit is this time-lapse video from a grad student from my same cohort who spent a lot of time in the mountains taking time-lapse or high-speed videos of blowing snow. So it's an incredibly chaotic process. This is a slowed down cross-section. So it's 6 centimeters wide, 3 centimeters tall is what your frame is actually capturing. And you can see in this blowing snow event, because there's a laser illuminating the pathway of all these particles, there's all this snow that's sort of bouncing around. It's crashing into each other. We've got this little tumbling piece of snow that's picking up and dropping things. And so we have this very chaotic, very violent interaction between airflow and our snow. And the long story short is, as our snow particles bash around, they get smaller. And when they get smaller, they end up entrained in the air. And once things get entrained in the air and suspended, they sublimate away. So the more exposure our snow, or whatever falls, has to wind, the more it is subject to these snow processes, and ultimately a decrease in your snowpack, because we can lose a lot of our snow back to sublimation. So the one thing you can do about it is to talk about your stubble heights. So this is from early on in my PhD, and we had sort of two cameras. One was on a 15 centimeter wheat stubble, and it's looking directly at another camera that was on a 45 centimeter wheat stubble. So you can see early on, our 15 centimeter stubble fills in with snow, and we can see these drifts marching back and forth. And it takes until about February before our 45 centimeter stubble is actually filled in as well, and it starts behaving the same way. But the reality is we had 3 months on our short stubble where we had all these drifts moving around. If we see drifts moving around, we've got blowing snow that's actively working. We're losing a lot of the snow back to the atmosphere directly, and it's not going to be available for infiltration in springtime. Okay, hold on. There we go. So the biggest factor when it comes to sort of managing snow and increasing the amount that's available to infiltrate in springtime comes down to stubble management. So there's things about stubble density, stubble direction, all of those things are important. But by far the biggest factor is how tall is your crop stubble. So anything that you can do to increase roughness on your landscape basically will suppress blowing snow, all that violent interaction between air and our snow particles, and basically suppresses that, and we end up with a much more snow accumulation. Less of it is blown away, and much less of it is sublimated back to the atmosphere. But it all really varies with your climate. So this is some work early on that kind of was looking at 4 different locations. Prince Albert, which is more, I would say, akin to Edmonton landscape, with being a sort of that Aspen Parkland boreal fringe. Yorkton, it's also a bit more of a rolling topography, wooded area. Regina and Swift Current, much more open landscapes. And so you can see how much your local climate will actually influence this. So if you have long open areas, you've got high wind speeds, you have the prospect for significant blowing snow, and therefore the ability to manage it with stubble is actually higher. And so this is an interesting lever that we sometimes are able to work with and sometimes not. There's kind of the complete other end of the spectrum when it comes to stubble management, questioning how high should we cut stubble versus stripper stubble is another sort of technique that's gotten a lot of favor in sort of southwestern Saskatchewan and southern Alberta, but basically has a different mechanism where it just strips the grain right off of the stalk. But what it also leaves behind is by far the highest stubble heights that you can possibly do. So this is some work that I did, I think, and did some snow surveys in 2023, I believe. And so looking at different crops with different stubble heights. So we had a durum that had a 25 centimeter stubble height versus a stripper canola that was about 90 centimeter stubble height. And in this situation, we really didn't see a huge difference in the snow water equivalent. The durum had about 53 millimeters of water, whereas the stripper canola was at 78. It really comes down to how much snow there is to begin with. If you don't have snow, you can't trap it. But there is a big factor in terms of when you do, how much can you actually trap? That same year, I was out near Concert, Alberta, and I was looking at a lentil field, which basically had no stubble, versus a wheat field that had about a 75 centimeter stubble height. And we had 110 millimeters of snow water equivalent in that wheat stubble, whereas the lentils stubble, it only had 41 millimeters. And that was the day after there was a snowfall, and it hadn't blown away yet. So the lever you have to manipulate and manage snow is it's quite a large one when it comes to stubble management. But you can be also creative. So not everything is stripper stubble or stubble height. This is just an image from some of the hayland I was working with a couple of years ago, and just leaving little strips of hay behind. Yeah, I sacrificed some of my hay crop, but in my mind, I was retaining more snow, and it was worth it. The other thing about all of this is that just because you have snow in a landscape doesn't mean it actually can get into your soil and be available for crop production. So this is where frozen soil infiltration dynamics are really important. So in a soil, as things get colder, obviously you have ice that forms in your pore spaces. There's always going to be some fraction of liquid water content in your soil, but the reality is that ice particles will form basically in the largest voids to begin with. And clearly, as you put solids into this matrix, the ability to transmit water through it decreases. So there is a significant decrease in the infiltration rates in frozen soils, but that's not to say nothing can make it in. So there's kind of some early work that was done in USAS days, looking at frozen soil infiltration. And so it really depends on the midwinter melts, fall soil moisture conditions for what is actually going to happen when it comes to snowmelt infiltration in spring. If it's a dry fall, if you've got very coarse, cracked soils, you can have a situation where everything will infiltrate. You'll have no runoff come springtime. Otherwise, you can also have a limited or a restricted situation where you can have a basal ice lens that forms after a midwinter melt, and no matter how dry it is beneath, everything will just run off. In between is the gray space, and in that, it really comes down to how much can infiltrate. It's a function of how your fall soil moisture content, were things dry going into fall, or did you have a late season rainfall that kind of created a saturated surface, or also how much snow is there to begin with. That also dictates how long snowmelt takes. So the longer snowmelt takes, generally the more will infiltrate as well. So kind of a high level overview on all of this, but just the takeaways that I'd like to leave you all with is that snow, it can represent a significant portion of crop available water in this landscape and climate. In years where you've got a high snow winter followed by a very dry growing season, it can be a significant, if not majority, source of the crop water that is used. And it can be ineffectively managed with our stubble management techniques, depending on what cropping system you're under. And then, at the end of the day, snowmelt recharge potential, it really depends on frozen soil infiltration factors. So how much snow is there even available to melt? You can't infiltrate what you don't have. And then as we get into years where, and this is one thing I've been noticing over my living experience here, is that we have an increase in midwinter melts. And this is kind of, it falls in line with a lot of climate change projections, which really focus on, we have increasing wintertime temperatures. And so now we're getting into these more ephemeral snowpacks at times. We have rainfall that happens in January. We had a very massive midwinter melt here a couple of weeks ago, that now we're getting into these situations where we have a lot more limited and restricted soil runoff driven factors. And then what are we looking at in terms of moisture come the fall? These are the major questions to ask, and we want to think about what the potential is and ultimately how to manage things. So I think with that, I think I am through my slides, and I guess we'll move on to the next presenter.
Thank you so much, Phillip. It was a fascinating presentation. Snow and stubble height and moisture levels. So obviously we'll come back to it after Monireh's presentation in our Q&A. So just as a reminder to the folks here, keep putting your questions in the chat so that we have a good collection of questions at the end to ask of both presenters. Our second presenter is Dr. Monireh Faramarzi, who is my colleague in the Department of Earth and Atmospheric Sciences. So good to see you, Monireh. She currently leads the Watershed Science and Modeling Lab that involves developing and applying physical and process-based tools such as hydrological, agricultural, and climate models to study water and food challenges, especially in the context of climate change. Her research focuses on assessing trade-offs and interactions between water and land resources, crop production, and geophysical drivers for environmentally informed management plans. So, Monireh, take it from here. Thank you.
Sure, thanks. I'm going to share my screen. I'm going to put this in presentation mode. So would you mind if you confirm whether you can see the full screen?
Yeah. Now it's good. Now it's good, Monireh.
Wonderful. Thank you very much, Sandeep, for the intro, and thanks for the invite to this presentation, to this event. So I guess what I'm going to do, I'm going to actually just use this laser points because it helps. So to build up on the first topic that was presented by Phillip, I think what I'm going to present on the effects of changes in winter hydrologic processes as soil moisture and soil phosphorus in canola agroecosystems in Canada. Okay, so the focus is on winter hydrology, soil moisture, and soil phosphorus, which is I'm gonna actually explain why. So before that, I'm gonna a little bit explain about the bigger context of the project. So this is part of what first of all, I shouldn't forget about this. So this work was completed. I should acknowledge this work that was completed by one of my PhD students, was recently published, Yinlang Huang, who did the majority of the work for this presentation that I'm going to do today. So this project or this work is part of this larger project, was funded by Alberta Innovates and Agriculture through their Agriculture Funding Consortium. So these are my project team members. The larger project is a 4 years project. And so the main goal of this larger project is to assess a nutrient smart, climate smart, and water smart crop productivity in Alberta, through which we have, of course, developed like kind of collaboration, partnership, and support with different kind of stakeholders in and outside of Alberta. So really the motivation for this bigger project is how rapidly the temperature is getting warmer, both air temperature and soil temperature. According to literature, a lot of reports, like the average temperature has increased by approximately 2 degrees Celsius, 1.9, since mid-1990s. And this is especially in Western Canada in prairie agricultural regions, which obviously it's nearly triple the amount of like global rates. And with this warming, hydrological processes have shifted, and it is reported that winters have become shorter, warmer, and a lot of changes in the winter hydrological processes itself. And it's also reported that, these changes in temperature has also brought about a lot of weather extremes, such as droughts and wet extremes, but droughts specifically have altogether have affected, in our agriculture, with implication to crop yields, to livestock production, and of course to economy as well. So with this in mind, we had several key or big questions in this project in the beginning. How changes in these climates, especially during growing season or non-growing season, can affect or have already affected agroecosystems, and how these changes affected soil nutrient dynamics. And because changes in nutrient dynamics have implication not only for crop productivity, but also downstream waters. And how and what are the implications to sustainability of global, like kind of our crop productions in Alberta and outside? And then if so, what are the adaptation strategies, how we can actually adapt to this changing environment and changing climate in our agroecosystem? So these are big questions, but we wanted to a little bit narrow it down in the first step. And our first question was how to actually study or how to develop a framework to assess, nutrient dynamics or changes in nutrient dynamics, and more specifically soil phosphorus in our agroecosystem under these conditions, these changes in general. So why phosphorus? Because phosphorus is one of the key elements for any plant growth, especially our crop production, and also because it supplies energy for transfer and cell structure, and it also kind of facilitates crop yield formation. We already know that this is very fundamental for any crop production. But in literature, when we looked at literature in the beginning, we found a lot of contrasting information. Some studies indicate that especially in Northern Hemisphere, in like kind of Canadian latitude, soil phosphorus is depleting in a very accelerating kind of rate, so that its depletion in soils are much more than, or they are exceeding its renewal, and therefore soil phosphorus depletion is going to be a major problem. But other sources of literature are actually kind of indicating that how soil phosphorus is accumulating in soils, and therefore they are impacting downstream water bodies. In other words, two groups of literature, some of them, they are actually kind of indicating soil phosphorus accumulation with implication to downstream water quality, because they are referring this accumulation into soil legacy effect, because once they are accumulated in a soil, they can be potentially transferred into downstream water bodies. And some other group of literature, they're actually talking about soil phosphorus depletion, which has implication to crop productivity. The more phosphorus, the more, potentially more growth, and therefore more productivity. So which one is the case in Canadian landscape? That was our first question to address. So digging into literature, we found that in fact, soil phosphorus is controlled by numerous processes, especially in the context of cold region, such as what we already have in Canadian prairie agriculture. So they are like soil phosphorus is actually kind of affected by hydrological processes, from soil temperature to soil moisture, snow melt, and so on. And also with crop physiological processes, so crop types and their stomatal conductance, photosynthesis, evaporation, a kind of mechanism, and soil biogeochemical characters. So soil itself, how is the chemistry in the soil, and how is the physics, and what are the physical properties of the soil can actually drive how nutrients and phosphorus can be actually kind of either accumulated or depleted from the soils. And on top of that, agricultural management, how we manage our landscape, our crops, tillage, residual processing, fertilization, and so on. They're all, all different sorts of mechanisms can drive how phosphorus or any other nutrients are accumulated or kind of depleted from our soils. So therefore, our goal, our interest was to understand, these mechanisms. So in other words, to quantify or to develop a framework that would systematically study how soil phosphorus changes under our agroecosystems by considering these processes into account. So our study area was Red Deer River Basin. So this is Red Deer River Basin. So this is Alberta. So the Red Deer River Basin is one of the headwaters of a bigger or larger river basin. Is named like Nelson River Basin. And this orange area, it covers most of this orange area, which is actually presenting our prairie croplands. And this region itself is extremely important region because it's considered as one of the world's major breadbasket because a lot of food commodities are produced and exported to over 170 countries around the world from this region itself. And Red Deer River Basin represents most of agroecosystem in this region itself. That's why we chose Red Deer River Basin itself to study with and to address that question. So this Red Deer River Basin, which is located in central Alberta almost, the watershed area is about 47,000 square kilometer. Elevation is very diverse, 500 meter to 1,700 meter in the agricultural region, and up to it can reach to 3,200 meter in the top mountains region. So most of this area is covered by agriculture or crop production. And then temperature varies from 2 to 34 degrees during growing season. Precipitation is about 250 millimeter during growing season, but year-round is actually 400 millimeter. And the snowmelt is reported that plays significant role in supplying water needs during early growing season, as also presented by Phillip. And soils, in terms of soil, so this picture shows soil groups. There are different soil characteristics and soil groups. And here, for example, in the most downstream region, we have drier soils, and these soils are named like brown soils, and these are like dark brown and black soils. And in this central region, which are dominated by dark brown and black soils, those are most fertile soils. And most of the crop density, as we are looking like crop density, most of the crops are actually denser in this region than in the downstream region, where is more probably more drier and the soil group is different. So in this study, so we chose rain-fed canola crop to study because this is one of the major or the most dominant crop grown, and not only in Red Deer River Basin, but this entire prairie region. So to address our questions, we need a framework. So our method is to use and develop process-based physical biogeochemical model because we want to actually be able to quantify or take into account or to simulate not only hydrology and plant growth, but also a number of processes related to soil phosphorus dynamics. So it's very complicated processes that we're hoping that by choosing this, we can actually address and take into account these effects when simulating, these processes, again, from crop production to hydrological change, winter processes into soil phosphorus mechanism itself. So we developed model, but we also verified our model with many different, best available field-based or reported data from crop yields, so which means our model was verified using crop yield data for 17 counties. So Red Deer River Basin has 17 counties. So for each county, we collected existing data, time series data for crop yields, for stream flow, crop from environment, Climate Canada, for example, for age stations, or also soil temperature data. We want to make sure our model is doing reliable job in simulating soil temperature data in 50 millimeter soil depth, 200 millimeter soil depth, and also 1000 millimeter soil depth. In addition to that, we also want to verify our model for soil phosphorus, because soil phosphorus is also simulated in the model. So I'm not going through details of these technical matters, but I just wanted to mention that we developed model with a lot of data, but also we verified model using these graph-based measurements. But this is the fun part that we wanted to actually learn. Now that we have a working model, we actually kind of extract data from simulated data from model to look at how soil phosphorus is changing across all of these counties. And no matter what county we're looking at, we found that the counties are following either one of these trends. So in these panels, x-axis is time and y-axis in the left is soil phosphorus dynamics, which is shown with this black line. So these small fluctuations are the seasonal variation, but there is also long-term trend. And we're looking at from 1993 to 2016. And some counties followed this kind of trend in terms of soil phosphorus, which we called it like stationary or equilibrium. We didn't really see a long-term trend change in general, but some counties actually showed declining trend in soil phosphorus, and other counties showed accumulating or increasing trend of soil phosphorus. So some counties are following like accumulating soil phosphorus, some are depleting over time, and some are kind of presenting more kind of stationary or balance. And we found that most of these counties that are showing increasing trend, they're located in most downstream section of the river basin, where they are actually covered by brown soils, and they are also drier. So now we want to actually kind of find out why is so, because when looking at this purple, sorry, I forgot to mention, in the right, like y-axis in the right, is the total soil phosphorus applied in the form of fertilizer. And in fact, while looking at how much fertilizer is applied, we found that while the pattern of soil phosphorus application through fertilizer is pretty much similar, not exact the same, but similar pattern, but still counties tend to show different patterns of accumulation or depletion across the region. Now, the first question is what is happening? How soil P pattern relates to soil moisture and soil temperature. So for this, we actually kind of using our model results, we looked at how soil moisture, soil temperature, and soil P export are different across these county groups. So here I'm showing, for example, in relation to soil moisture, as you can see, this is declining county groups, and this is showing the increasing or accumulating group, and this is the stationary. So y-axis is soil moisture. As you can see, the accumulating counties, they tend to show the minimum amount of soil moisture as compared to the other counties. And by the way, we're also differentiating how these amounts are different in the past, from past to most recent decades. So because we're interested in understanding decadal change as well. But regardless of these decadal change, just comparing how county groups have different soil moisture pattern, the increasing group or the groups that are accumulating soil phosphorus tend to have much less soil moisture. And then when looking at soil temperature, we found that the same group tend to have higher temperature or warmer temperature. So therefore, our first conclusion was that drier and warmer soils tend to accumulate soil P, whereas wetter and colder soils tend to deplete soil P. And most of these drier and warmer soils, they are actually located in downstream region of the, in the watershed. And what about soil P export? What it means is when there is a runoff, there is a potential that some of this soil phosphorus can be exported or transported through runoff to downstream water bodies. And we found that the same group, like accumulating group, they're exporting more phosphorus to downstream water bodies. However, before we expand on this and into the details, I want to also mention that we found that regardless of what the mechanism is in terms of the pathway or mobilization pathway, plant uptake is always the major cause or the reason or the mechanism that would actually remove soil phosphorus from the soils. So if you look at both declining, increasing, or stationary county groups, it's soil like plant uptake that would dominate the majority of the phosphorus removal from the soil, which makes sense because plants need phosphorus, and therefore during their growing season they would need to take phosphorus. However, the county groups that are more wet, that phosphorus can be more available for plants. Therefore, more phosphorus is removed in those groups, in those depleting groups in the central region of the Red Deer River Basin. So, but the next question is, how about winter processes? Is winter hydrologic processes making any, playing any role, or how changes in winter hydrological processes because of these probably climate change over the past 2 decades have actually caused changes in phosphorus availability and therefore implication to crop productivity and downstream water quality. So winter hydrologic process. To address this question, first we wanted to see if winter processes are actually changing in the region. So what we did, we performed comprehensive analysis of how snowmelt timing is changing across all these counties. So we have 17 counties. We're interested in understanding how snowmelt timing during wintertime is changing by comparing it from past to most recent decades. So the conclusion, I'm not going through the details of this technical, a lot of complexity here in these figures, but in general, we found that generally or at the regional scale, the snowmelt timing is shifting about 2 weeks towards earlier time when you compare the most recent decade, which is shown with the red here, with the most, more earlier decade. So snowmelt timing is shifting towards earlier time, no matter what county you're looking at. That's the first observation using our model results. The second question was related to winter time. We want to know whether soils are actually getting warmer, because a lot of people are talking about winter processes are changing. The same factor that we're interested in is to really quantify how and if it's changing. So winter soil temperature. So again, we perform analysis for each county group, and x-axis here is winter temperature, and y-axis shows whether the changes from this past decade to the most recent decade has been more positive, indicating more warming, and or more negative, indicating it's getting colder. And we found that, so these dots are indicating the counties within each of these county groups. So we found that no matter which county group you're looking at, the majority of these counties are experiencing warmer soils. In other words, we found that winters are getting warmer among all county groups and more among accumulating groups. So this is the counties where actually they address more increasing P trend, and they are getting warmer in general as compared to the other county groups. And the number three kind of mechanism related to soil, related to winter processes that we were interested in actually looking at was freeze-thaw cycles. Because as also mentioned by first presenter, freeze-thaw cycles, according to also literature, has indicated that it's changing and it's becoming more frequent, but we actually wanted to quantify this for our study region. And we performed analysis for all of these county groups, and we compared how they've been changing from 1993, from the past decade to the most recent decade. So the y-axis here is showing the total number of cycles. And we found that no matter what county group we were looking at, or most of the counties, this frequency of these cycles are increasing in the region during winter time. So far, associated with winter time, we found that snowmelt time is shifting towards earlier time, and soils are becoming warmer during winter, and freeze-thaw cycles are becoming more frequent during winter time. But then the question is, if the region is already experiencing all these changes during wintertime, does it affect soil phosphorus dynamics, like soil phosphorus runoff towards downstream water bodies? We want to actually investigate that. I'm not going to explain all these details. I just want to mention that we perform deeper analysis for each county, and the x-axis is the total soil phosphorus export from these, because of these wintertime processes only. We're just filtering out the growing season. We're only looking at wintertime processes here. And we found that, probably I'm summarizing all these results in this more simple to understand or easy to understand kind of picture. So as you can see, for all county groups here, the y-axis is the soil phosphorus export, or in other words, soil phosphorus transport because of wintertime runoff processes or wintertime soil warming and freeze-thaw cycles. And we found that when you compare the 2 decades, almost in all county groups, the soil phosphorus export is increasing, but it's increasing much more in these accumulating groups, which are located in downstream region of the basin. And so these county groups that are accumulating over time soil phosphorus, the warming or change of hydrological processes during winter is actually kind of accelerating soil phosphorus more in these regions than the other regions in the river basin in general. So to summarize, key finding is that drier and warmer counties, they tend to accumulate soil phosphorus, whereas wet and colder counties, they experience soil phosphorus depletion or balance situation. So it seems like moisture and temperature is a key driver here. And then primary pathway of soil phosphorus mobilization is plant uptake, but plant uptake is already driven by soil moisture. Where there is no soil moisture or drier environment, especially in downstream region, even plant uptake is not significant. That's why it causes accumulation of soil phosphorus in the soil, and therefore potentially playing like as a they are acting as a legacy source for downstream water bodies. And winter processes are secondary, are playing definitely role, especially in accumulating county groups, but they are secondary to plant uptake. Just if you compare the magnitude-wise. However, as I already mentioned, changes in the snow processes and the snow regime and the snow runoff is affecting more this accumulating group, and they are becoming more source of phosphorus export to downstream water bodies. So this work was published most recently in a peer-reviewed journal. So I guess I'm happy to take any questions. We have further questions based on this study. Now we're investigating, okay, now that we understand how soil moisture is regulating soil phosphorus, either depletion or accumulation, we're also interested now to use the same framework and to assess how different crop diversification can either accelerate or even kind of, reverse these trends across region, and how climate change in the future and the different global warming scenarios are going to impact these trends across the regions. So based on that, I'd like to thank our funding source and our collaborators and our partners. So I'm very happy to take any questions. And thank you very much for your attention as well.
Thank you. Thank you so very much for your presentation, Monireh. Learned so much myself. The interactions between, phosphorus levels in the soil, the moisture and the temperature. So thank you. At this time, I invite everyone to ask questions. We have only a few minutes left, but put your questions in the chat box or raise your hand, and we will have your questions be put to the presenters. So as many of you are still having your creative juices going, I'm gonna field a couple of questions here to our presenters. So Phillip, I was thinking about what you said about the stubble height and perhaps about the stubble management could help in terms of retaining snowpack, and that could then help crop yield and so on and so forth. But the height of the stubble varies quite a bit depending upon what the crop is, right? So wheat may have and a canola may have much higher stubble versus, let's say, lentil or something like that. I just wanted you to explain. So does that mean that we should not be producing lentils, or are there other ways to then manage snowpack?
Yeah, no, I'm not going to suggest that we go to a monoculture cereal only cropping system whatsoever. Um, no, it's a very valid and is a point, and it's a challenge to manage, right? So we need crop rotation for many agronomic reasons. And yeah, there's stubble height is one aspect that's important. There's things about residue cover as well. So we may not have standing stubble when we harvest a pulse crop like lentils or peas, but we'll have significant residue, which is important to maintain as well. I didn't really talk too much about that. And then it's also an aspect as well is just in your rotation, where are your crops accessing moisture from, right? So pulses tend to be more shallow rooted and have smaller crop water demands, whereas a canola and a wheat, for example, they can have much deeper rooting depth. So knowing where one is in your crop rotation and the residual moisture that is being left behind is a part of the strategy to overcome. So yeah, you can retain more snow in some years with certain crop types, and you're going to lose some of that potential in others. But then there's also creativity that people can have. So, maybe you're doing some intercropping. Maybe you are doing, strips side by side, different things. I've seen many different creative ways to manage snow in those sort of contradictory crops.
Okay, well, thank you. I see one question here from Greg. Greg, do you want to say your question, or do you want me to use my voice?
Oh, go ahead. Use your voice. Thank you.
Okay. All right, Greg. So Greg's question is, how can we use your work this is to Phillip you. How can we use your work to help increase snowmelt runoff to help fill Alberta's dugouts and reservoirs? For example, where to place snow fences in terms of winter prevailing winds?
Yeah. So it's not necessarily my work, but there was a lot of work done from various different sources. Some other John Pomeroy and others, Division of Hydrology back in the day in USask, they did a lot of work around how do we design snow retention stuff. So there is a lot of ways. There's a lot of information available, which tends to be older stuff, of how to design your optimal snow fence in terms of how, the configuration, how porous do you need it to be, how tall, sizing it with respect to your potential snow accumulation. Yeah, there's lots of things you can do, but yeah, snow fences are a great tool if you have, perpendicular to your prevailing wind direction. If you know approximately how much snow that you're going to be getting, you can size it accordingly. How tall you need to build, and then you can also get estimates of what, when this thing fills up, how much snow might actually be available to melt, so you can start matching your snow fences with respect to how big your dugouts that you're trying to fill are downslope. So yeah, there's a lot of stuff out there around snow fences, for example, that can help guide those decisions. So it's not just a random guess like, maybe I build it this big and where do I put it? Maybe over here. Like there is stuff out there.
Okay. Thanks, Phillip. Monireh, I was thinking your presentation, and I was wondering if you could talk a little bit more about, you talked about, the changing levels of phosphorus and how it's connected to the moisture and the runoff and temperature rise and things. How is it affecting the crop yield in the counties that you have studied?
Yeah, so we didn't specifically look at relationship between them, but because crop yields are higher in the central region, like kind of for those counties that are depleting soil phosphorus, and because they are more moist as well, and therefore soil phosphorus is more available to plants because they are more bioavailable to plants, and then they have higher yields and in general as compared to the accumulating county groups that are located in more downstream regions. But nevertheless, there are a lot of factors playing a role in the long-term increase of soil phosphorus, from droughts to management, and so on.
Okay, no, thank you. All right, any other question? I see one from Richard. How does double density and uniformity affect snowpack? Say row spacing. This is to you, Phillip.
It's an aerodynamic problem if you want to get into aerodynamic physics. So at the end of the day, stubble density, uniformity, and even direction, they will play a role, but at the end of the day, it's generally what matters the most is if the wind is being displaced. If the wind speed, the airflow is being displaced above the surface, doesn't really matter. Once you get to a certain level of roughness, it doesn't really matter how it's oriented or whatnot. It's going to be displacing the wind flow vertically away from the surface, and that's all that really kind of matters. So it doesn't matter as much as height. Perpendicular rows that are perpendicular to prevailing winds will be more effective at retaining snow on your landscape. But as anyone knows, prevailing winds are not the same as actual winds. And so you can have a single event that comes in from a different direction and it can negate any of those potential gains. So it's really event specific. But yeah, where you'll see impacts of row density and uniformity and even direction, that sometimes shows up a bit more in terms of your snowmelt behavior. So it may have a similar amount of snow to begin with, but if we have a lot of radiation-driven melts, a lot of solar radiation early on in the year, that's going to create a lot more melt right around our stubble stalks, and so you have a very sort of highly heterogeneous within your stubble rows melt, versus sort of later on in the year if things are warmer and it's more of a sensible heat, energy from the atmosphere, from the air temperature. Those ones will be a little bit less sensitive to your stubble configurations. So that helps. I just threw in a link here for Greg if he really wants to go down the path of trying to size his snow fences accordingly. There's some fun equations in that link.
Thank you. Thanks for sharing that link. Monireh, a question for you. We were talking earlier, and we were talking about climate change and such, and our sort of discussion went into the direction of perhaps irrigation could be a way to adapt. It could be used as an adaptation strategy. Do you want to expand that a little bit more?
Absolutely. So based on this initial step of the study, we found that definitely soil moisture there was the bold message that soil moisture is a driving a mechanism for how soil phosphorus is accumulated, and therefore with implication to downstream water bodies, or depleted with implication to more productivities and towards increased yields. But now exactly, that's actually a very proper question. Can we then suggest irrigation as potential mechanism to add more water into the soils, especially in these dry environments, to help with both reducing accumulation and therefore preventing those sources, and second, use soil phosphorus towards more productivity? I would say it's a little bit difficult to say, because it's a difficult question, because while theoretically adding more moisture through irrigation sounds to be a really good source to buffer these climate variabilities, new source of water towards like plant productivity, crop yields. But on the other hand, we should realize that these environments, like these dry environments, often they have like more alkaline soil, because these are how soils develop, these high pH during these low precipitation time, which has been frequent over many years. Now, if you add water in these regions, because these soils are really rich with calcium, because their pH level is high, these very alkaline or calcareous soils. What happens, soil phosphorus, if you add irrigation and also fertilizer applying like phosphorus into the soil, this phosphorus is gonna react with calcium most probably, and then it's gonna generate like more stable form of phosphorus mineral, which won't be available directly for plants, and it's gonna be even further accumulate in these regions. But on the other hand, we know that soil water is gonna probably reduce kind of pH or increase the acidity level in the topsoil. But again, when you think about root zone or root depth in the lower soils where they are still rich with calcium, probably it's not gonna help. It's gonna even probably aggravate the situation in terms of accumulation. But these are really under theoretical thoughts, and until we are not really examining this in the actual, regions, I would say I don't know unless we actually kind of do this. And frankly, this is one of the questions that we're very much interested in, and when talking to numerous people to find the potential funding sources and partnership to actually examine, because we have the framework, we just need to expand the study focused on addressing this as potential adaptation strategy in these regions.
Mm-hmm. No, thank you very much, Monireh. Aisha, is there a room for one more question here, or are we?
Our time is up, but if everyone's okay to stay for an extra second, we could. That's up to our speakers and our attendees.
I'm okay with that.
Yeah.
Okay. So there is a question here, Phillip. This is for you. Could agroforestry be an option for retaining snowpack?
Yes. That's the quick answer. There's define agroforestry because people have different perspectives on that. But at the end of the day, you can sort of take some learnings that came from sort of forestry situations and shelter belt related studies throughout the prairies. And yeah, anytime you are reducing wind speed, you're going to have increases in accumulation. But, whether are you looking at a shelter belt situation, then it becomes how important your spacing of shelter belts is important. So where is there a net increase versus now we're just creating more challenges in logistics? That's a bit of a trade-off. There's a lot of work that's been done on the forestry side where it's like looking at, say, thinning of trees. So what is the optimal distance for clearing sizes to maximize the amount of snow collection? But then you kind of feedbacks with some of the other physics involved. So it's always a give and a take. Agroforestry, sort of forestry-based things, we may have a lot more snow retention in a snowpack because it's not subject to wind speeds once it's there. But you have to be careful if snow is being collected in the canopies, depending on your trees, because then we have a lot of sublimation and often even negates the impact. So it really depends on the outcomes. Agroforestry is a really wide spectrum, but absolutely there's a role for it. It's just a matter of what configuration are you talking about? What are your goals?
Excellent. Thank you, Phillip. Aisha, take it away.
Okay, we're going to wrap up there then. Thank you so much for your time and expertise, Monireh and Phillip. Thank you so much for moderating, Sandeep. The recording of this session will be made available in the next few weeks on our website. So if you're wanting to look back and reference the presentation, you could do that. We will be holding more free lunchtime webinar sessions, so keep an eye out. And thank you everyone for attending today's session.
Thank you very much.